So we come to the last topic of our discussion or the syllabus, which is basically the scattering theory. The basic idea, as I have told you in the very beginning, behind scattering theory is very simple. That means that there is an object that you want to understand. So, what you do is that you throw something else at this object, and by analyzing how that something else bounces off that object, you can get some information about the object itself. So that is the principle behind scattering theory. So therefore, scattering is a valuable probe to study the structure of particles when basically you cannot see them. Okay, so you have known about all these collision between electrons and protons and heavy elements or the nucleus of heavy elements. So these kind of objects you cannot see, but what you can do is that you can throw something at a heavy nucleus, and then from that information that you get out of that experiment would be useful to study the structure of a nucleus. For example, it is through scattering experiment that one can learn the hydrogen atom consists of a nucleus and an electron going around it. We know that electrons are basically kind of point particles also from the results of scattering experiments. Furthermore, the scattering experiments have also told us that protons consists of yet another constituent which is known as the quark. Therefore, we can clearly see that the scattering is an essential tool in our understanding of the quantum nature of particles. So we have to spend some time studying this topic, and this we have to study in the realm of quantum mechanics. But let us actually begin by recapitulating some of the features of scattering theory in classical physics. I am more or less certain that in your classical mechanics course this must have been discussed, but if not, let me very briefly mention this to you such that you can get some idea. Okay, classically, the simplest scattering that we can consider is that of a beam of a particle from a fixed center of force, or in fact, if you do not want to think about force, you can simply think about a very heavy ball, billiard ball, and then you throw something at this ball, and then you see how that something, the other object actually behaves after it gets scattered from the billiard ball. So to study this kind of scenario, we will first think about the Hamiltonian that we have at our hand. So the Hamiltonian that we have is basically always have the form p square by 2 mu plus Vr. I have written this mass of the particle as mu simply because at later part of our discussion we will again come back to a scenario where we will have to use the YLM theta phi, where m was the azimuthal quantum number. So we have actually specified that symbol m to denote the azimuthal quantum number and mu for the mass of the particle. Now you can have two different interpretations of this Hamiltonian H, which I have written here. One is that this represents the motion of a single particle which is moving in a fixed background potential V of r, and this kind of setting or this kind of scenario is basically appropriate for Rutherford's experiment, where you basically fire an alpha particle at a gold nucleus. So all of you are familiar with Rutherford's experiment at your +2 level. There you remember that Rutherford did this experiment to study the gold nucleus, and on the gold nucleus he actually had fired some alpha particle to figure out what is there in the gold nucleus and what are the result of the scattering. So this kind of scenario is best described by the fact that this Hamiltonian being treated as the motion of a single particle which is moving in a background potential V of r. What is the second one? The second interpretation is that this Hamiltonian represents a relative motion of two particles which is separated by a distance r. And these particles are basically interacting via a force field which is a conservative force field, which can be written as minus gradient of a potential. So we can take, say for example, V of r to be the Coulomb potential to describe the scattering of electron. So these are the two different scenarios which we basically broadly classify, our Hamiltonian into. So we will mostly use the language which is suitable for the first interpretation that I have mentioned, that means this one. But keep in mind that everything basically holds, whatever we discuss for one basically holds for two also. Now once your Hamiltonian is decided, then you ask the question what to calculate. So you are already familiar in your PH 204 course about the calculation of scattering in case of one-dimensional potentials, and you calculated there the reflection and transmission coefficients. But in 3 dimension we need to replace this reflection and transmission coefficients by something which is a little bit more complicated, and we will see what these are. But before that, as I was telling you, what is that we actually are looking for classically. So classically what we do is this, that we can think of a fixed center of force. You can think of a, say, charged particle of infinite mass or very heavy mass, and if the particles that are being thrown towards this heavy particle which is charged, then these particles, if they are being scattered, you can think of these particles which are being thrown at this charged particle as electrons or protons also. And we will assume that a beam of particles is basically incident on the fixed source of force. So this fixed scattering center, a charged particle, can be this one, and the trajectories of the particles change due to the force experienced by these particles which are being thrown at, and this force is experienced by this scattering center, presence of this scattering center. And suppose that all these particles which are basically thrown at this scattering center are thrown along, say, the z axis, and these trajectories of all these particles will basically change because there is this scattering center sitting here. So the initial trajectory, if we now take a single particle among all these particles which are being thrown at, suppose you throw a single particle, forget about a swarm of particles at the moment, a single particle with kinetic energy E, then the initial trajectory is basically characterized by something which is known as an impact parameter, and which is always denoted by B. What is an impact parameter? An impact parameter is basically the distance which is closest to the particle could get to the scattering center. So it is a distance which I have shown here in this figure. If the scattering center was not here, then this particle which is thrown at a height b could actually be going unhindered without any change of the trajectory. But now that it has actually come towards this vicinity of a scattering center, as I said, this may be a charged particle, this may be another charged particle, so it will basically be scattered. And because of the presence of this force field at the scattering center, or because of the potential that is there in this point, if this particle cannot reach very close to this scattering center, rather it will get scattered in a different path, and the distance what is the lowest distance or the minimal distance it can reach close to the scattering center is known as the impact parameter. I have also used this term scattering center. It can be, as I said, the scattering center, it can be a proton fired at a heavy nucleus, and then the nucleus is the scattering center. So whatever which is fixed, static, and whatever which is having a very heavy mass such that it does not move under the influence of the other particle, that object is generally termed as the scattering center. Now the particle emerges with scattering angle theta. What is this scattering angle theta? The angle between the asymptotic incoming and outgoing trajectories are known as scattering angle. So this is the ingoing trajectory, and this is supposed to be your outgoing trajectory. Now this is your changed trajectory because of the presence of this scattering center. This is your ingoing. But if this scattering center was not there, then this would have been your trajectory which this particle would have followed. So the ingoing and outgoing trajectories, so this is your outgoing trajectory, this is your ingoing trajectory, and the angle that this makes with this asymptotic incoming and outgoing trajectories are basically the known as the scattering angle. Now you assume that the target is very heavy and the trajectory remains in one place. Then you can ask this following question, that given the impact parameter, what is the scattering angle? So that is the question that you need to answer. Or given the angle, other way around, given the angle, what is the impact parameter? It's the same question. So by solving the classical equations of motion, you can find the theta, the scattering angle, as a function of the impact parameter and the total kinetic energy of the particle, or you can calculate the impact parameter in terms of the scattering angle and the kinetic energy of the particle. So as an example, as I said, I was thinking of a billiard ball which I have drawn here, and then suppose that the target in our case is a billiard ball of radius r, and the incident particle mass m, having mass m, it bounces off elastically. There is a elastic collision, and in terms of the angle alpha, if you look at the figure very closely, then this is your b, which is the impact parameter, which is nothing but r sine alpha. So your b is r sine alpha, and the scattering angle obviously is this, because if this ball was not there, then this would be the outgoing trajectory, and then this is your incoming trajectory. So this is the change in the trajectory. So that angle that it makes with this between this incoming and outgoing trajectory is basically incoming and outgoing trajectory is basically your angle theta, scattering angle theta. So there you can clearly see from this figure that theta is pi minus twice of this alpha, because this is an elastic scattering. You have this angle as alpha, therefore this is alpha, and this also is alpha. So pi minus 2 alpha is your theta, therefore alpha is pi by 2 minus theta by 2, and you can replace this alpha here, and therefore you can find out your impact parameter in terms of the scattering angle theta, which is r sine pi by 2 minus theta by 2. So if this is r sine pi by 2 minus theta by 2, then you can immediately say that you have written your impact parameter. Your target was to write the impact parameter as a function of the scattering angle theta. So this is r cosine theta by 2. So that is what you have written. Now you can say that if my impact parameter was greater than r, then of course your theta would have been 0, because the particle would simply come and it would simply pass away of this. So suppose your impact parameter is somewhere here, it would have unchanged, did not change its path. It should have gone without any hindrance. On the other hand, if your b is less than equal to r, then you know that theta can be written as a function of impact parameter b. Now, more generally, particles incident within an infinitesimal patch of cross-sectional area d sigma will scatter into a corresponding infinitesimal solid angle d omega. This is something which is very important, because this concept, this formula will be required later on. So let us understand this part a little bit more carefully. So what here we are looking at is that, suppose I have a stream of particles which is incident within an infinitesimal patch of cross-sectional area d sigma. Suppose this is that d sigma area patch that we are looking at. And these particles which are falling within this patch of infinitesimal patch of cross-sectional area d sigma will therefore actually scatter into a corresponding infinitesimal solid angle, d omega, which is this. So this is basically the area here which subtends a solid angle here. So if you look at this is a zoomed in version of this region. So here what you are doing is that lot of particles, they are coming in. You are just taking an infinitesimal patch of cross-sectional area d sigma, and you want to figure out what will be this number of particles that actually passes through this d sigma and scatters into a corresponding infinitesimal solid angle d omega, because there is a scattering center somewhere here. So here again what you are taking is that you are taking the uniform beam of particles, each having kinetic energy E. Remember, we are dealing with classical scenario so far, and each particles having kinetic energy E falls within an infinitesimal patch of cross-sectional area which is shown here. Therefore, you can actually calculate this d sigma. How can you calculate this d sigma? For example, you know that there is a impact parameter b, and this impact parameter b actually changes from b plus db within this small infinitesimal area d sigma. So this is b, the lowest number, lowest distance of approach that one can get into, and then this is dB, the maximum that another particle can take if my beam of particle is actually lying within this circular patch, suppose. Now therefore you can immediately write d sigma as b times d phi. What is phi? Phi is this angle. So b times d phi times dB. Then b times d phi times dB is going to give me the infinitesimal patch d sigma. Now the particles within d sigma will now evolve to lie in a cone of solid angle d omega, because as all the particles through this patch comes in, they all scatter into different angles like this because of the presence of some scattering center here, and we have assumed spherical symmetry of the scattering center. So d sigma d omega we know is sine theta d theta d phi. If you want to take a look at this, you can actually see here closely. Here is that patch, and you just add all the corners whatever angle that it makes here, solid angle it makes here, it is basically your d omega, which is nothing but sine theta d theta d phi in terms of the infinitesimal angular coordinates. Therefore, now you can actually define something which is known as the differential cross section. Differential cross section is basically d sigma d omega, and because you have now written d sigma and d omega both in terms of your known quantities, then you can immediately write this as b by sine theta mod of db d theta, which you can denote as curly d theta, which is basically a symbol to denote differential cross section. So why there is a modulus sign, why there is this absolute value sign? This is simply because since theta is typically a decreasing function, your theta is this one. Here we have shown theta and d theta as well. Since theta is typically a decreasing function of b, the derivative is actually negative, and therefore this absolute value sign is here. Now this quantity d sigma d omega can actually also be thought of as a ratio of the scattered flux by incident flux, where flux is defined as the number of particles per unit area per unit time. So whatever comes in, so this is the incident flux and then this is the scattered flux. So the ratio between them is also thought of as d sigma d omega. Now, once you have obtained this differential cross section, you should ask the question, what is the total cross section? That means total area of incident beam that is scattered by the target. So the total cross section is basically the integral of d theta over all solid angles. That means you have to calculate this quantity d theta d omega, and d theta you know already that this is d sigma d omega. So d sigma d omega is your sigma total. Now what happens if we now look back the hard sphere scattering that we have discussed here? So the hard sphere billiard ball scattering we have discussed here. In fact, by the way, this is basically known as hard sphere scattering. So this is one representative example that everyone actually discusses at the beginning of such scattering issues, scattering discussions. So we have discussed that. Now we also need to apply these definitions that we have defined, that we have obtained now. So we recall the hard sphere scattering and we remember that this impact parameter is basically related to the scattering angle theta by this relation. B is r cosine theta by 2. And then immediately we know that we also need to figure out what is dB d theta, because that is what we are getting from here. So dB d theta is basically nothing but minus r by 2 sine theta by 2. And as we have seen, we have already said that dB d theta generally will be negative. So d theta, the differential scattering cross section, should be b by sine theta mod of dB d theta. And then we actually substitute all the things. For example, b I can write in terms of the scattering angle theta, which is r cosine theta by 2, and then mod of dB d theta is nothing but r by 2 sine theta by 2, which is here, and therefore this is r square 2 cosine theta by 2 sine theta by 2 by 4 sine theta. I have just multiplied the numerator by 2 and put a 4 here, such that I can write it as sine 2 theta by 2. So this is sine theta. So the sine theta gets cancelled and what we get is r square by 4. But this, we have to remember, is an unusual example where this d theta, the differential scattering cross section, is independent of theta. That is something which generally doesn't happen. Then once we have obtained this curly d theta, the total cross section we know d theta d omega, curly d theta d omega, which is nothing but r square by 4 d omega. But then d omega, we know the solid angle is basically sine theta d phi, where theta is integrated from 0 to pi and phi is integrated from 0 to 2 pi. So if you integrate this, the result that you will obtain is pi r square. But isn't that expected? It is expected because it is the cross-sectional area of a sphere for the hard sphere scattering, particles incident within this area will hit the target and those further out will miss it completely. So that this is somehow understandable. But the good thing about the formalism that we have developed here is that it applies just as well to soft targets also. For example, instead of a hard sphere, if I have a Coulomb field of a nucleus in that scattering center, that are not simply a hit or miss, those cases also are actually going to be covered by the same formalism. But in that case, for example, here it happened that this d theta didn't depend on theta. So for those cases, it will be a function of theta. Now we can also interpret this scattering cross section in terms of something else. For example, if we have a beam of incident particles with uniform intensity, or sometimes it is called luminosity, L basically gives you the number of incident particles per unit area per unit time. The number of particles entering the area d sigma, the infinitesimal area d sigma, and hence scattering into the solid angle d omega per unit time will therefore be dn should be equal to L d sigma. Why? Because L I have defined as the number of particles, incident particles per unit area per unit time. So if you go back and look at this figure, if I have a count of the number of particles entering this d sigma per unit area per unit time, then if I multiply with d sigma, that is going to give me the total infinitesimal number of particles crossing that d sigma area. But then d sigma, remember, d sigma d omega is your capital D theta. So I could as well write this L d sigma as L curly d theta times d omega, where d theta is the differential scattering cross section and d omega is the solid angle. Therefore, you can write d theta, curly d theta, the differential scattering cross section as 1 by L dn d omega. This is of course another way of defining the differential cross section, and this defines d theta in terms of quantities which you can measure in a lab. That is why this formula is even more useful, because in a lab you can measure this n, you can measure the luminosity, and using this formula you can therefore calculate the differential scattering cross section. So we will stop here before starting the quantum mechanical scattering, because I think that this is something, the classical scenario, which needs some of your which needs some time for you to look at, because quantum mechanical scattering, when we start, will be a little bit more mathematically involved. And also I want you to look at the one-dimensional examples that you have already done in your PH 204 cases, because what we are going to do here is basically all the three-dimensional calculations. But I request you to actually look at the one-dimensional examples as well as the S matrix approach that was discussed in there.